Have you ever stretched a rubber band, held it there, and felt it sort of lose its fight over time? Or maybe you've seen an old plastic gasket that used to hold a perfect seal, but now it's just given up? Well, that's not just the material getting tired. It's a very specific and predictable physical phenomenon. And today, we are going to pull back the curtain on the science behind it. So here's our game plan for this explainer. First, we'll talk about the kind of weird idea that materials have a memory. Then we'll define exactly what stress relaxation is and look at how scientists model it. After that, we'll see how the test is actually done, dive into a really surprising case study, yet it involves chicken, and finally, we'll wrap up with why any of this matters in the world around you. All right, to really get why materials seem to get tired, we have to start with a fundamental property that a lot of materials, especially polymers, have. It's a mouthful, but it's called viscoelasticity. So let's go right back to that rubber band. You stretch it and bam, it fights back instantly, right? But if you just hold it there, stretched out, you start to notice something. The force you need to keep it stretched actually goes down. It feels like the rubber band is just giving up. And the scientific reason for that feeling? That's viscoelasticity. You know, viscoelasticity is just the perfect mashup of two different properties. You've got the elastic part, which is like a spring, it snaps back right away. Then you have the viscous part, which is more like honey. It flows slowly and resists motion. So when a material has both of these traits, how it behaves really depends on time. And that's where this whole idea of a material having a memory comes from. What you did to it in the past affects how it's behaving right now. Okay, now that we have that foundation, we can zero in on the main event, stress relaxation. This is one of the most important ways that viscoelastic behavior actually shows up in the real world. So here it is, the official definition. The two things you absolutely have to remember are constant strain, that means the material is stretched to a certain point and then held there, and decrease in stress, which means that internal force, the fight back from the material, gets weaker and weaker over time. Picture this. We take a piece of plastic and we stretch it by, say, 10%, and we do it instantly. If you were looking at a graph, you'd see a huge, immediate spike in the stress. But then, as we hold that stretch perfectly steady, the stress starts to decay. It drops fast at first, and then it kind of levels off more gradually. That curve, that slow letting go of internal force, that's stress relaxation in action. Now, it's really, really important not to get stress relaxation mixed up with its close cousin, creep. They're related, but different. With stress relaxation, the stretch is constant, and the internal stress fades away. With creep, you apply a constant stress or load, like hanging a weight on something, and the material slowly and continuously stretches over time. See the difference? Same family, different conditions. So, how in the world can we predict this stuff? It seems pretty complicated. Well, scientists have come up with some really clever, simple models to help us visualize what's actually happening inside the material.
The building blocks are actually just two simple things. First up, you've got a perfect spring. This represents the elastic part. You can think of it like the chemical bonds between atoms stretching. They store energy, they want to snap back. And second, you have a dashpot. Just picture a piston moving through a cylinder of thick oil. This represents the viscous part, those long polymer chains slowly sliding past each other. It's slow and it dissipates energy. Now, this image here looks pretty complex, but the core idea is simple. By hooking up these springs and dashpots in different ways, we can create models that do a surprisingly good job of predicting how these materials are going to behave. It's a really powerful way to understand that intricate dance happening between all those polymer chains. Okay, so let's look at the Maxwell model. It puts a spring and a dashpot, one after the other, in series. Now think about what happens. If you suddenly stretch the whole thing, the spring extends immediately. That creates stress. But over time, the dashpot, which represents those sliding chains, slowly starts to give. And as it does, the spring can contract a little, and the overall stress fades. It's a perfect, simple picture of stress relaxation. But if you connect them differently, like side by side in parallel, you get the Kelvin-Voigt model. Now, if you apply a constant force, that viscous dashpot fights against the spring's desire to stretch right away. And what's the result? A slow, gradual stretching over time. A different arrangement that brilliantly explains a totally different phenomenon, in this case, creep. So we've got the concept, we've got the models. But how do engineers actually measure this stuff in a lab? Well, it turns out the test is pretty straightforward, and it is absolutely essential for designing products that last. It's really just a three-step process. You take your material, you apply a constant strain, and then you sit back and measure how the stress decays over time. And this isn't just for a science fair project. This is a standardized industrial process, governed by things like the ASTM D6147 standard. It is so important for elastomers, the materials used in seals and gaskets, where you have to know exactly how long they'll keep pushing back before they relax too much and fail.
All right, I know this has all been a bit abstract, so let's look at how this exact science solved a truly bizarre problem in the food industry. And I promise you, this is fascinating. So here's the problem. There's a condition in broiler chickens known as wooden breast. It's a muscle disorder that makes the chicken breast really hard and unpleasantly tough. As you can imagine, this causes huge economic losses. So researchers needed a way to make this meat more tender. And, this is key, they needed a way to precisely measure if their treatments were actually working. So check out this data from their experiment. They took this tough chicken meat and zapped it with ultrasound at different power levels. Now, just look at that highlighted row for 600 watts. The hardness dropped from over 3,600 grams of force all the way down to about 2,600. That's a huge difference. The data clearly showed the meat was getting softer. And how did they confirm this? You guessed it, they used a stress relaxation test. By measuring how quickly the stress inside the chicken samples faded away, they could put a hard number on the meat's texture. A faster stress decay meant a more tender piece of chicken. And as the researchers themselves put it, stress relaxation was an amazing tool for predicting meat texture. That chicken example is pretty wild, but let's zoom back out for a second. Understanding stress relaxation is absolutely critical in just countless areas of engineering and design. I mean, seriously, think about it. That rubber gasket in your car's engine? You have to know how well it's going to maintain its sealing force after years of being compressed. If it relaxes too much, the seal fails, and you've got a big problem. What about the vibration damping pads in your phone? Their whole job relies on their viscoelastic properties. From bolts holding up a bridge to components in a satellite, being able to predict and manage stress relaxation is just vital for safety and reliability. So, the next time you see an old plastic chair that's starting to sag, or a rubber seal on a container that's just lost its springiness, you'll know exactly what's going on. It's not just getting old, it's undergoing stress relaxation. Which kind of makes you look around and wonder, what other objects in your world are slowly, silently relaxing right now?